Dear friends, today I am going to take about the superscalar operation. In this category, we have to see cache memories, performance considerations, virtual memory, secondary storage, program parallelism, and shared variables, multi-computers. First, we have to see what is a parallel processing. A more aggressive approach is to equip the processor with multiple processing. So in this case, so many processing elements are used. That is multiple processing elements. Each processing element will do individual operation, individual task. Therefore, we can complete multiple instructions at a time. At a time means these will happen during only one clock cycle. So only one clock cycle, multiple processing elements, multiple instructions, so that multiple tasks are executed, completed during only one clock cycle. So with this arrangement, several instructions start execution in the same clock cycle, and the process is set to use multiple issue. So issue means instruction. Each processing element will be supplied with individual instruction. Such processors are capable of achieving an instruction execution throughput of more than one instruction per cycle. So throughput is defined as number of instruction per one clock cycle. Normally, for one clock cycle, one instruction. But here, due to the availability of multiple processing elements, suppose if we are using 100 number of processing elements, then throughput is equal to 100 issues divided by one clock cycle. Therefore, total throughput is equal to 100. So, throughput is increased as much as a number of elements we are using. They are known as superscalar processors. Next one. This is diagrammatically explained in this slide. First one, instruction fetch unit. And then here it is, instructions are kept in queue in this block. And then dispatch unit, the outputs are going to floating point unit, integer unit. And then these two outputs are written by using write results block. Here we have used only two processing elements. A processor with two execution units. Two processing elements. One unit for floating point operation and another unit for integer operation. So in the above diagram, there is a processor with two execution units, one for integer and another for floating point operation. The instruction fetch is capable of reading the instruction at that time and storing them in the instruction queue. So in the previous diagram, we have seen one block. In this case, there are so many instructions kept in queue, and the instructions first taken will be from in this direction only, not from the opposite direction. So one by one it will be taken out. In each cycle, the dispatch unit retrieves and decodes up to two instructions from the front of the queue. So this is the queue and this is the front end. Next one, if there is one integer, one floating point instruction and no hazards, both the instructions are dispatched in the same clock cycle. So we are assuming that there is no hazards. Hazards are described as data hazard, instruction hazard, control hazard, structural hazard. If these hazards are not appearing, then the two instructions will be executed in the same clock cycle very correctly. Advantages of superscalar architecture. The compiler can avoid many hazards through judicious selection and ordering of the instructions. So the instructions are kept in order in queue. In the above, the compiler should strive to interleave floating point and integer instructions. This would enable the dispatch unit to keep both the integer and floating point units busy most of the time. In general, high performance is achieved if the compiler is able to arrange program instructions to take maximum disadvantage of the available hardware units. So in this case, due to the multiple processing elements, we can achieve high performance. And disadvantage of superscalar architecture. In a superscalar processor, the detrimental effect on the performance of various hazards becomes even more pronounced, because in the in the previous slide we have assumed that under the absence of the hazards, many processing elements can perform multiple tasks during only one clock cycle. But unfortunately, if any one of the hazard is present, then superscalar processor efficiency will come down. Due to this type of architecture, problem in scheduling can occur. Main memory is memory on which the computer works currently. So now the next one is cache memory. Once the power is off, data will no longer stay inside the memory. So that is random access memory. Our main memory is nothing but random access memory. Secondary memory, it is external memory. So it is primary memory, main memory, and external memory, so external to the computer system, is secondary memory, and it is not as fast as main memory, but data stays permanently. And when compared to the processor speed or cache memory, the main memory speed is very slow. Even the secondary memory speed is still slow when compared to the main memory. If CPU needs to read or read data instruction from the memory, then first cache is examined. So for this, whenever CPU while doing the execution, it needs data immediately, it will not go to the main memory. It will examine the cache memory. If the data is available, it will be taken and the execution will be completed. Suppose if the data is not found in the cache memory, then CPU moves to main memory. So cache memory will store most frequently used data, and it is easily accessible. It is very fast. It is smaller, so Cache memory will not store all the code or data. It will store the important data, very often needed data. If the word is found in cache, it is known as cache hit. If not found, then the cache miss information data cache miss. The performance of the cache memory is measured in terms of hit ratio. So anyway, speed is involved, then we have to use the speed as performance parameter. So here cache is as fast as possible. Therefore, the performance of the cache is measured in terms of hit ratio. So hit ratio, already what is hit? If the data is found, then hit, catch hit. So hit ratio means, what is the formula? How many times it is accessed, the number of times the data is found is called as hit ratio. In case of cache hit, the time required to access data from cache is known as cache hit time. The time required. So automatically it is said that cache hit time will be very less. Very less time for accessing the data from cache. Hit ratio is equal to, hit ratio is H, it is equal to hit, total number of hits. That means total number of available data, availability of data divided by hit plus miss. Total number of hits happened, total number of miss happened. So the addition of both, and it is equal to, the hit is nothing but number of hits, and hit plus miss means total number of access that happened from the cache memory. So hit is number of available data, number of times the data is available. Hit plus miss means total number of accesses CPU had done. Next one, miss ratio is the fraction of accesses that are not in the cache. So we have to mention in terms of the probability of having the miss. It is equal to 1 minus hit. So 1 minus hit is, hit means hit. In case of cache miss, the time required to fetch the required block from memory is known as cache miss time penalty. So, and actually what will happen? CPU goes to cache. Suppose if the data is not available, available means execution smooth. Not available means it will go to the main memory, and the same data will be, definitely it will be available in main memory. It will be taken while coming back to the execution. The data will be stored in cache because for the later use, for further use, and then coming to the execution. So that automatically the time for fetching the data is more, because it has to reach to main memory, and secondary it has to store it in cache, and then third it is coming for execution. For these three it takes some time. This time is at most time delay only. So this time delay is known as cache miss time penalty. Then average access time. Average memory access time, it is equal to hit time plus miss rate into miss penalty. So hit time we know. Time required to take the data from catch. And miss rate we know. It is 1 minus h. And then miss penalty. So miss penalty means by definition we know the time taken to fetch the data from main memory. So it is equal to average memory access time TA, it is equal to hit. So hit time H into TC. So TC is cache memory access time plus 1 minus H. So 1 minus H is miss ratio already we have seen into TC. So TC we know cache memory access time plus TM. TM means data taken from the main memory. The time at which data taken from the main memory. It is equal to, so TC is common, TC plus 1 minus H into TM. So here 1 minus H into TC. Here H into TC. So it is equal to HTC minus HTC. Therefore, 1 into TC is present. That is why TC plus remaining thing 1 minus H into TM. TC we have already done. And then miss ratio 1 minus H, it is equal to. So miss ratio is probability of having the data miss. So 1 minus H is written in terms of previously H equal to hit divided by. So in the same way, miss ratio is equal to catch miss divided by total accesses, hit plus miss. So number of miss, catch miss is equal to number of miss divided by it is total access. Total access. Catch performance can be improved by using higher catch block size and then reduce the miss penalty and reduce the time to hit in the catch. So already taking the data from catch is less. Still, if we reduce the time to reach the data and if we are reducing the miss penalty ratio, so miss penalty means the time taken to reach to the memory. So the almost whenever the CPU request data, it should be available in cache. If not, it should go to main memory. That sin we have to avoid. If we avoid, if we overcome, then automatically miss penalty time will get reduced. So next one, performance considerations. Performance of a memory system is crucial in memory organization as it has the effect on overall system speed and efficiency. So total CPU performance will be primarily depending on the memory only, memory accesses only. So in simpler way we can tell that memory performance. The key factors include access time. So access time means accessing the cache, capacities, the data size and cost, all of which influence the design and implementation of memory hierarchies like cache, main memory and secondary storage. So storage, I meaning that memory. We can simply say memory system is divided into so many levels. So main memory and processor memory. Already registers are inbuilt in the main memory, in the processor, CPU. So first level registers, second level main memory, third level cache and fourth level Fourth category, secondary storage. So first one, so if we order them in accordance with the speed, first level is processor register, second level is cache, third one is main memory, fourth one is secondary, because it is ordered in terms of the speed. Memory register so speed as fast as high, as fast as um, I mean the speed is much more, and the a little bit less speed is for cache, and then main memory totally less speed. And if you take secondary memory, still it is slower than the main memory. Understanding these factors is essential for optimizing performance and balancing cost effectiveness. So let us have a look at memory hierarchy. A memory hierarchy is designed to provide a balance between speed and capacity. How it is balanced? Fast memory, small fast memory located very close to CPU. So this is very important. Already I told you that it is small fast, but its location is very nearer to CPU. For that, one small example we can say, so suppose if it is a keyboard and 0, 1, 2, 3, 4, 5, 5 is located here. In the keyboard, 5 is located here. But this 5 is most commonly used number and it is stored in cache. The access time for 5 will be very less from the cache, and it will take more time to go to main memory, and it has to search for the address of the data. So it will take more time and it is supplying the data in a delayed manner. And main memory, so normally the data will be lost once if the power is shut off. That is why it is called as volatile memory, and the name is random access memory. So main memory type is random access memory and it is volatile memory. So voltage is present, the data will be retained. Voltage is lost, the data will be lost. So now, what is the feature of the main memory? It is larger module and slower and for general data storage and instructions. So main memory is used for storing the data as well as instruction. So instruction means program code, and it holds data and instructions actively being used by the CPU. So CPU access will complete the data and instructions uh, instruction taken away from the main memory to the CPU. So it holds the data and instructions actively being, which will be used by the CPU. Secondary storage, for example, HDD, SSD, large, slow, and inexpensive. So if the speed is increased automatically, the cost for the manufacturing of the memory unit will be more. But here secondary storage, large size, but accessing the data is in very much low speed. That is why it is inexpensive. Performance consideration at this time. So first one, this is the time taken to retrieve data from main memory location. Shorter access times are desirable for faster performance. So main memory means we cannot say it is slower, and faster performance we cannot obtain. Next one, capacity. The amount of data that can be stored in the memory. Larger capacity allows storing more programs and data. If the size of the memory is large, then automatically we can store the data bulk and then instruction code also, program also. Next one, cost. The price of memory chip which influences the overall cost of the system. So what is the manufacturing cost and how far it is influencing the speed and capacity. And next one, memory system design and optimization. So in this case, cache design, factors like cache size, associativity, so the relationship between the main memory and cache memory, and replacement algorithms play a significant role in cache performance. So these are all the base for increasing the performance, for getting the better performance of the cache. So main memory technology, choosing between static RAM, that is SRAM, and dynamic RAM, DRAM, depends on the performance requirements and cost considerations. So first one, memory management system. Techniques like virtual memory. So virtual memory, it is not connected physically to the memory system. But whenever we need the memory system to be expanded, so the task requires more memory space, then virtual memory will be used. And paging help manage memory resources and improve performance by allowing programs that are larger than physical memory to run. So the techniques like virtual memory and paging. So paging is the address calculation, help manage memory resources and improve performance by allowing program larger than the physical memory to run. So it will allow the big program for running to get execution. Example, catch performance. The effectiveness of catch is often measured by its hit ratio. Effectiveness is measured in terms of hit ratio. And improving catch performance involves strategies like catch size, using faster access method, and implementing efficient replacement algorithm. Virtual memory is computer architecture technique that extends the effective memory available to a system by using parts of the hard drive as an extension of RAM. So extension of RAM. This allows programs to access more memory than physically present in RAM. So we already specified the addresses of the RAM, but beyond that defined capacity of the RAM, we can use that storage is known as virtual memory storage, enabling the execution of larger programs. So no need to fear about that the execution will abruptly affected by using the large number of codes, large number of steps. No need to fear for that. And multiple applications simultaneously. Virtual memory technique is used in computer OS. Virtual memory uses both hardware and software to enable a computer to compensate for physical memory storage, temporarily transferring data from RAM to disk. So for that temporary transfer from RAM to disk, we can use the virtual memory. So in virtual memory system, the program or data are first stored in the auxiliary memory. First stored in the auxiliary memory. portions of program or data are brought into the main memory as they are required by the CPU. So, CPU will execute the program and data which are execute the program using the data, but the CPU will access the program or data from the main memory only. So a virtual memory block is known as page. That memory block, memory space is called as page. And virtual memory which is known as page fault. In the page also, if CPU does not find the data, then it is known as page fault. Virtual memory is a concept used in some large computer system that permit the user to construct programs as though a large memory space were available. So, before using a larger code, the user may not have hesitation that the memory is sufficient. Memory is having sufficient location, because even if it is not sufficient, it can use the virtual memory. It gives programmers the illusion that they have a very high memory, although the computer has small memory. So they can feel that. So computer has smaller memory, but for usages, he may get very huge memory size. That is why he is thinking that whether it is true or false. Actually, the computer size, memory size is very less. But how come we are getting such a large expansion of the memory for our larger code? Virtual memory is a portion of logical memory from physical memory. It creates the function of programming easier because the programmer no longer requires virtual memory when multiple physical memory is available. Advantage. It helps to gain speed when particular segment of the program is required for the execution of program. So where for the two for dedicated part of the program, this is used. This virtual memory concept is used. It compensates for the lack of physical memory. So memory size is less, not sufficient for doing the executing the big program. Then automatically it has to take the virtual memory for that. Some sequences will be there. That is why it compensates the lack of physical memory. Helpful in implementing the multi-programming environment. So simultaneously we can execute multiple issues or multiple instructions. It allows you to run more applications at once. More applications at once. You can run larger application with less real RAM. So suppose in between, if it is not sufficient, it can take over the virtual memory. That is why you can boldly start large task execution. Can be inexpensive and can hence enhance data security also. So virtual memory finds application in security purpose, and it is expensive and inexpensive, because cache memory speed, it is costly, but virtual memory is inexpensive. Disadvantage: it is slower than the physical RAM. So physical RAM, when compared to that, secondary memory is slow. In the same way, virtual memory is also slow. Like, it takes more time to switch between applications. So whenever applications change, then for switching over from one to another, it may take time. It may cause stability problem. So stability problem may appear. Does not offer the same performance as RAM. So we cannot expect the same performance of RAM with the virtual memory. It may take up precious storage space which may be used otherwise long-term data storage. A virtual memory system provides a mechanism for translating program generated addresses into correct main memory location. So it is used for the calculation of the memory address maximum. Then address space, a small diagram for the virtual memory. Yeah, an address used by the programmer is known as virtual address, and set of such address is known as address space. And then memory space. An address in main memory is known as physical address. So it is normal and accessible to the user. But when we are using virtual memory, the memory address will be different. For that, we have to calculate. We means the CPU has to calculate the address of the data. And a set of such location is known as memory space. So it is address space and it is memory space. Memory is known as physical. Set of such location is memory space. So here virtual address, logical address, either both names are correct. Address space, address generated by program. So it is truly available. Suppose if we are using the virtual memory, the address has to be mapped to the main memory. So that is why mapping stated here. And this is memory space. Memory space means physical address, and then it is actual main memory address. This address is actual main memory address. It is address generated by program. Both will be operating in coordination. A table is then needed to map a virtual address of 20 bits to physical address of 15 bits. So normally physical address is mentioned in terms of 15 bit. So 15 bit address. But virtual address it is 20 bit address. Suppose both are uniform 15 or 20, then mapping will be easy. But memory address is of length 15 bits. But virtual memory address length is 20 bit. So compulsorily they have to be mapped to get the original address. The mapping is a dynamic operation, that is, every address is translated immediately as a word referred by, and is referenced by the CPU. So here secondary memory, and it is divided into fixed devices, removable devices. And fixed devices they further divided into hard disk device, CD or DVD drive. And removable disk is divided further categorized into pen drive, blur, uh, blur, Blu-ray disc. Blu-ray disc. Secondary storage in computer system provides persistent and large capacity data storage. So it is inexpensive, therefore it is large storage. Unlike primary, which is volatile, and it is non-volatile. Secondary non-volatile, but primary RAM is volatile. It is essential for long-term data retention and is typically slower, cheaper per storage compared to primary storage. So retention means we can retain the data for long. Then key characteristics of secondary storage. Non-volatile. First one, non-volatile. Data remains stored even when the power is cut off. Large capacity. It can store significant amount of data ranging from megabyte to petabyte. and then cheaper per unit storage. So for this less expensive than primary memory unit of storage capacity. Slower access. Access times are generally slower than primary memory. So primary memory already I showed an example. If 5 is a record, it has to go into deep. But here no need. Not directly accessible by CPU. So CPU cannot access virtual memory, secondary memory directly. So it will not be connected directly to the computer. Data must be transferred to primary memory before CPU because CPU can access only memory and virtual memory cache memory, not secondary memory. That is why we need to transfer the data from virtual memory to main memory by using. For that only we have used the page and page. Page will map the virtual memory to main memory. Virtual memory size is 20 bit, main memory size is 15 bit. Both are non-uniform, therefore mapping is to be done. Then types of secondary storage. First one, magnetic storage. So hard disk drive use magnetic media to store data, offering large capacities and lower cost. And second one, optical. CD-ROM, DVD, and Blu-ray disc store data using optical laser technology. So optical means it is obviously costly, suitable for storing large amount of static data. So it won't occupy the space. That is why large amount of data it can store. Next is solid state devices and USB, universal serial bus. Flash drives you utilize flash memory, offering faster access speed and greater durability compared to the traditional magnetic storage. So next one, other storage media. Magnetic tapes, paper tape and punch cards are the older technologies that were used for secondary storage. Applications of storage, secondary storage, operating system and application storage stores the operating system and other software applications. And then data archiving and backup provides long-term storage. So secondary storage, once if we store the data, we can edit up to that and the data will be available there. That is not actively being used by the CPU. User files and documents stores documents, images, videos, and other user-generated documents. Then, next topic, program parallelism and shared variable. So, the concept parallelism involves dividing a program work into smaller. So pipeline stages we have seen the program is divided into instruction is divided into 5 stages. Instruction fetch, execute, decode, execute, write back, like that we have C. In the same way, here also the task is a large single task is divided into smaller number of subtasks, independent parts that can be executed concurrently. So each will execute separately but at the same time. This can lead to the significant speed up. So see, speed up factor will increase. If one processor doing 10 work, 10 processor if you are using one time 10 processor is you completing the 10 stages of a task. So the speed is reduced to 10 times. If you are not using multiple processor, 10 times more. 10 task means 10 times more. So this can lead to significant speed up, especially for computationally intensive tasks. types: bit level parallelism. Operations are performed in multiple bits of data simultaneously. Then instruction level parallelism, multiple instructions are executed in parallel, often through techniques like pipelining. Multiple instructions are performed. Here, multiple bits of data are operated upon. Next one, data level parallelism. Different parts of the same data are processed simultaneously by different processor. Different parts of the same data will be so a big data is available. That big data is divided into, sometimes for example 5, one data set is divided into 5 processes will be used, and different parts, 5 different parts will be used by the 5 different processors, so that the time speed up will be reduced to 5-fold, 5 times. Task level parallelism. Different tasks or functions are executed in parallel. So by the name itself, we can tell which one is parallel. Next one example, pipelining. A sequence of instructions is broken down into stages, and different stages are executed simultaneously. Multi-threading. A program can have multiple threads. Thread means it is having a instruction, the part of the instruction, that is thread. Multiple thread of execution, showing parts of the program to run concurrently. So in the same way, multiprocessing, processors and different processors can run on different processors, each with its own memory space. Different processors can utilize different processors, each with its own memory. So the processors cannot go anywhere. It is having its own memory. So the process will be completed within itself, not searching for data from out. Overhead. First one, parallel processing introduces overhead in terms of communication between processors. So many processor means they are in a task, big task we are using. So there must be a relationship between the processor. So relationship, how it will be maintained through the communication only, because one processor may need the data from the another processor for execution of the current execution. For that, the required data will be sent from the processor when it is giving out the request. Next one, managing synchronization. Load balancing, ensuring that all processors have a similar amount of work can be a challenging. So we cannot tell that all processor will have the same work, same load, same task load. We cannot tell. Synchronization, but we cannot tell means at the time all the processors are used, so they should operate in coordination with one another, means they have to be uniform. Suppose if so uniform means they have to be loaded with the same amount of data, same amount of execution time. If they vary from processor to processor, then it will be a challenging one. It cannot cope up with the speed and correct solution. Synchronization, coordinating the action of multiple thread or process. So thread means process only. One instruction is divided into. So in one instruction, suppose 10 number of operations are there, then it can be divided into 10 number of thread. Each thread is performing its own process or calculation. To avoid a race condition and other problem is crucial. And then shared variable. concept. Shared variable or memory location that are accessible by multiple processes or threads. So suppose if we have processing elements, number of processing elements of 5 can share the global main memory. This allows for communication and coordination between these concurrent entities. So through so what is the main through communication only. So how two processes can interact with one another, for that an interconnect network will be provided. So directly it cannot. So two processor, the processor one cannot take the record data from the processor to directly through the communication network only. It will get directly, but through the, so it has to go to the communication network and then taken back. So for this what we need so in this way, suppose through the communication network it is done, then coordination will be maintained because of the speed problem only. Processor 1 is more speed, processor 2 is less speed, means the transfer of data will get affected. So if it is directly, so whenever it is giving, the second one is able to take immediately. Suppose if it is delay and not taking the data, another data will come and edit this, I mean that replace the original old data. That is why I said that communication network will be required for interaction. Next one, importance data sharing. Data shared variables enable processes to share, such as results from calculation or global state. So suppose first instruction is add R1 comma R2. Second instruction is uh, move first instruction add R1 comma R2 comma R3. Second instruction is R second instruction is R1 sub R1 comma R2 comma R4 R4. So what is the meaning here? This R1 is nothing but the result of addition of the previous instruction. So it has to be supplied the input from the previous expression. That is why if it is not getting the executed result in correct time, the whatever the available data with the R1, with that this subtraction operation will get completed. That is why if two instructions are independent on one another, that the time synchronization should be possible. Possible synchronization they should get. Then only the data requirement will be correct. In time it will get the correct data whether it is solution or not. If it is solution, it has to get it at the right time. Challenges: race condition. Multiple processes attempting to modify a shared variable concurrently can lead to the unpredictable results. So shared variable means many things. If it is requiring data from the previous, only data means no problem, but the result data means it is serious problem. That is why it is stated here, multiple processes attempting to modify shared variable concurrently can lead to unpredictable result. So data inconsistency, ensuring that all processes have a consistent view of shared data can be can be completed. So deadlock processes can get stuck waiting for each other to release shared resources. So either data can be shared or resources can be shared. whatever it may be, the particular will be obtained by the processor whenever time comes. The correct time it should get. It may be shared or not shared, but correctly it should get it. That's all the problem here. Next, locks and semaphores, mechanisms to control access to shared resources, preventing multiple processes from accessing them simultaneously. This is locks. And then atomic operation, instruction that guarantee that an operation is performed as a single individual unit, preventing race conditions. So single from individual unit, indivisible unit, preventing race conditions. So what is here stated here, if suppose instruction is very small and it cannot be divided into, then it will be easy for the processors, but it may be many same instruction many times, but it will not be divisible, it will not be separable, then it will be operation will be smooth, it will avoid the race condition. Main memory barriers, instructions that ensure the memory operation are performed as a special order, preventing data inconsistency. So suppose if data dependency, so depending on the result from the previous execution, the same thing should be considered while designing the architecture. If it has happened, then no problem. We can prevent the mistakes in the instruction that ensure memory operations are performed in a specific order, preventing data inconsistency. Then, interplay between parallelism and shared variables. So when multiple processes or threads are running in parallel, they often need to access shared variable to communicate and coordinate their action. Proper synchronization, this point already we have seen. Proper synchronization mechanism are crucial to ensure that shared variables are accessed and modified correctly, preventing race condition, other synchronization issue. So this also we have told. If it is expecting the result from previous, it should the first should be executed in correct time. Then only the second instruction will get the correct data. Otherwise, whatever the data available previously, it will not be removed, and with that previous older data, it will execute the current instruction, and the output will be automatically wrong. Understanding the interplay between parallelism and shared variable is essential for designing different and reliable parallel programs. So next one, multi-computer. So multi-processor means so many processing elements they are all controlled by the main CPU, main processor. But a multi-computer means each computer will have its own processing element. Multi-computer in communication organization refer to system where multiple independent processors, each with its own memory, communicate and cooperate to solve the problems. These processors are connected via interconnection. So in the previous case also, one processor to multiple processing element also, they will have the interconnection network through which the communication will happen. In the same way here also, multiple computers, multiple processors with their dedicated memory. So if the processor has to communicate, suppose if the processor wants the data from the processor 1, P3 needs some data from P1, it has to send the message request to message passing network, and it will indicate the processor 1. With the permission of processor 1, the concerned data will go to the processor 3. So these processors are connected via interconnection network, typically employing message passing. So in the previous case, we have used the technical term interconnection network, but here that network is differently called message passing network. Multi-computers are a type of distributed memory, multiple data architecture, MIMD architecture, multiple instrument, multiple data architecture. It is a distributed memory, MIMD architecture. So SIMD means shared, MIMD means distributed. So in this way, the multi-computers are differing from the multiple processors. And one more thing, the interconnecting network is differently called as message passing network. So here, there the memory is shared from the global main memory. But here each processor, they have their own dedicated memory. That's all in this lecture. Dear all, we can see in the next video, and with this we are almost completing all the topics of computer architecture, and in the next video we will see the problems related to the shifting operations and the pipelining operations, and performance of the system, how to calculate. With that, we will do the problems in the next video. Thank you all.